contained in a cyclotomic field. So it's elementary in the sense that it only uses facts from a first level algebraic number theory class, no class field theory, no local fields. But there is some background required. So most people here I see like no algebraic number theory. If you don't, so I wrote out some facts that I'll be using. Namely, right, if you have a finite extension of Q, little k, and big K, which is Galois over that, then if we take a prime in K, it splits in big K. So P is a prime in K, beta lies over it.
Hey, Julian, duck for YouTube.
It's going to split as a product of the conjugates of beta under the Galois group to some power E.
Sorry.
Where, what?
Okay.
You have the convenient formula that EFG equals N, the size of the Galois group, where F is the degree of this field extension. Also, I should point out the notation I'm using is from the paper that I read, and it's kind of based on German. So Z for decomposition group, T for inertia group is German.
Hey, can you tell us what paper you read?
Yeah, this is an elementary proof of Kronecker-Weber Theorem. It's from the AMN. And so when you have this setup, when you have a prime sitting in little k and beta sitting above it, you can define what's known as the ramification groups. So Z, the decomposition group, that's the set of Galois elements which fix your prime. And the higher ramification groups, the VI's, are the ones which permute things mod powers of beta. So this is true for all x in OK. And so if you've never seen this stuff before, you're going to get a descending chain of subgroups, which are actually all normal in Z, I guess. For convenience, V0 is used a lot, so it's singled out as being called the inertia group. Z is the decomposition group. You're going to get a descending chain which stabilizes after a finite number of steps at 1. And some facts about these I presented here. So none of these facts are too hard to prove, but just so you can follow later on, Z mod T is isomorphic to the Galois group of the finite field extension there. In particular, it has to be cyclic. This is a finite field extension.
What's the tilde for?
Tilde, so
I'm sorry. You don't
it's OK mod beta, right? So you're modding out by the maximal ideal. It's a finite field.
Yeah.
The size of the inertia group is E. The size of the decomposition group is EF. Those constants over there. The index of the decomposition group in G is little g. And some facts that I'm going to use. So if you look at the fixed field of the inertia group, and you look at the prime beta T, which is just taking beta and intersecting it with that fixed field, that prime is going to be unramified over P, and beta is going to be totally ramified over that prime. So I didn't mention this. Totally ramified means that E actually equals N. There's one prime raised to the nth power. Unramified means that E equals 1. And smug? Yeah?
Oh, hey, I forgot what the decomposition group is.
That's Z. That's the definition right up there.
Oh, it's on the top of the board.
Yeah.
Okay.
Everything is contained here,
Okay.
except ramified, what that means. Ramified means that E is greater than 1. So if you look at V0 mod V1, it actually lives inside the multiplicative group of this finite field. In particular, it's cyclic. That's a cyclic group. And for higher J, this is J bigger than 1, bigger than or equal to 1, the quotient Vj mod Vj plus 1 actually sits inside the additive group, K tilde. Right, so if this is a finite field of size, Q, then the size of V0 mod V1 divides Q minus 1. Here, the size of Vj mod Vj plus 1 divides Q. Some other things to note. So Minkowski's theorem, if I have a finite extension of Q, which is not actually equal to Q, then you can actually find primes which ramify in that extension. That's going to be useful. Cyclotomic fields. So if I join an mth root of unity, the Galois group is going to be the units in Z mod MZ. In particular, if I look at zeta of P to the rth root of unity, P is the only prime that ramifies in this extension. And last but not least, this was something we talked about. So if I give you two Galois extensions K and L over Q, then is actually Galois as well. And the Galois group of the composite sits inside the product of the two Galois groups in a very natural way. So if you look at elements of this Galois group and that Galois group, which have the same restriction on the intersection, that's actually what the image of this group is going to be. Okay? That's right. So I have a lot of information packed into this talk, so it's kind of condensed facts. Okay, so to prove Kronecker-Weber, I'm going to start with a few lemmas. So the first one says that, right, in this situation here, so actually maybe I should give a little addendum, right? So here in this setup, little k tilde and big K tilde are finite fields. So, right, so little k tilde is going to have size some prime raised to a power, and right, what's the size of this? Well, this is going to be q to the f. Right, so I mean, if f is the index, then it's going to be q to the f. And fact 3 over here says that, well, v0 mod v1 sits inside the multiplicative group of big K tilde. So the multiplicative group of big K tilde that has q to the f minus 1 elements. So just from this fact over here, you could say, well, the order of this group divides the order of that one. It divides q to the f minus 1. But in the case when you have an abelian extension, actually something better than that happens. So the first thing is that, and I'm going to state this without proof. I'll give you a suggestion as to how you would prove it. But if I look at the decomposition group and I mod out by the first ramification group, if this is abelian, right, in this setup over here, then you can say something better about the size of v0 mod v1. Then right, so a priori, we know that the size of v0 mod v1 divides q to the f minus 1. But actually, in the case when this is abelian, and this is very general, in our situation, all extensions are going to be abelian, so this condition isn't even necessary. But if you know that z mod v1 is actually abelian, then v0 mod v1, well, it's a cyclic group, and its order divides q minus 1. And so, I mean, how do you go about proving such a thing? Well, I'm not going to give the full proof, but so, right, what is, right, so z mod t, z mod v0 is isomorphic to the Galois group of big K tilde over little k tilde. So you can take sigma in z, which is for the Frobenius map, in z mod t, mod v0. Right, so the Galois group of a finite field extension is generated by a Frobenius automorphism. And you can take tau in v0 such that the image generates all of v0 mod v1. In v0 mod v1, tau generates this group.
v0 mod v1 is sick.
Yeah, v0 mod v1 sits inside the multiplicative group, so it itself is cyclic. So it's generated by some tau. And then I'm not actually going to do this out for you, but an easy calculation